Again, welcome to Mathematics 164 Precalculus. And this is lecture 4-2, which cover our textbook chapter 4, session 2. In this lectures, we're going to discuss about linear programming using the graphical methods. So our main objective again is linear programming using the graphical methods to find the optimal value of linear function subject to constraints. Again, use the graphical method to find the optimal value of a linear function which is subject to constraints. So we start first with the feasible regions and solutions. Here we say that a linear programming is a technique that can be used to solve problems like the one posed in the application preview. Again, if the limitations on the variable called the constraints can be expressed as linear inequalities, and also the function that it is maximized or minimized, called the objective function, is a linear function, then this program is called a linear programming problem. Again, we are going to see an example soon. So the linear programming is widely used for businesses, problems, and also economics problems also, which normally involve many variables. Sometimes it can be more than 100 variables. In this our lectures, again, we are going to use only 2 variables. So in this session, we begin our study of this important topic by considering problems which again involve only 2 variables for now, which can be solved again using the graphical methods. Now, the constraint forms a system of linear inequalities in 2 variables, whose solution now will determine a region that's any point of which may yield the maximum or the minimum optimal value for the objective function. Hence, any point in the region will be determined by the constraint, which we call the feasible solution, and also the region which we call the feasible region. And the best way to solve this problem is by a good example. So here we have an example. In this diagram, we can see that we have a linear function because we have 2 straight lines. So we have 2 linear functions. One is 2x plus y equal to 8. The other is x plus y equal to 50. So normally the concept here is that we have 2 functions with 2 variables. So again, it's a linear function. The higher exponent is 1 for both variable x and y. The exponent is 1, so it's a linear function. If it's 2, it becomes non-linear, such as a parabola function. So here we are going to graph our first linear function, then our second linear function. Now, graphing a function, especially a linear function, all we need is 2 points, the x-intercept and also the y-intercept. X-intercept means when y equal to 0, what's the value of x? And x-intercept means when y is 0, what is the value of x? Y-intercept means when x is 0, what's the value of y? So for example, here we have 2x plus y equal to 28. Is the same as writing y equal to 28 minus 2x. So when x is 0, it means y is 28. So we do this concept and we plot our graph. So after we plot the 2 graphs, we have to again consider the region. The region also will be based on the constraint, the boundary. So we have region for 0.010, 10.8, 14.0, and the region, which is 0.0. So any points in this region area will satisfy our condition. That's what we call the closed and bounded region. The closed, based on the condition, the inequality of the equation. So let's see a very good example soon. We'll see a very good example soon. So the solution of linear programming problem is when the feasible region for the linear programming problem is closed and bounded, as we can see, the region here is closed and bounded, the shaded area. Then the objective function has the maximum value and also the minimum value. Now, when the feasible region is not closed and bounded, then the objective function may have only either a maximum only or a minimum only or no solution. So normally when it's bounded and it's closed, for example, here we can get both minimum and maximum solution, the optimal minimum and maximum. But when it's not again closed, and bounded, then we may either find only the maximum or only the minimum or neither of them. But we cannot find both maximum and minimum. We only find both maximum and minimum if it's closed and bounded, the feasible region. Now, the third said that if a linear programming problem has a solution, then the optimal, which is the maximum or the minimum value of an objective function, will occur at the corner of the feasible region, which can be determined by the constraints. And then the fourth is that if the objective function has its optimal value at two corners, then it also has that optimal value at any point on that line or the boundary connecting those two corners. The best way to solve this problem or to understand the concept is to solve the problem. This is a very good example here. So the example here on my right side, that's example. The left side will explain the procedure, step by step. So here, for example, they say we should find the maximum and the minimum value of C equal to 2x plus 3y. So C equal to 2x plus 3y is our constraints. This is subject to the constraint of s plus 2y less than or equal to, okay, so this is our condition now. S plus 2y is less than or equal to 10, 2s plus y is less than or equal to 14, and s should be a positive value, also y should be a positive value, which means s should be greater than or equal to 0, y should be greater than or equal to, so this will be our constraints. We are dealing with only the positive side of s and y. So the first thing we should do is to try to plot the line for s plus 2y less than or equal to 10 and 2s plus y less than or equal to 14. Normally, we are going to plot the graph as s plus 2y equal to 10, 2s plus y equal to 14. We plot the two straight line. Then from there, based on the s is greater than or equal to 0, y is greater than or equal to 0, we are going to shade the area that meets this condition, only positive value for s and y area. So let's go with the steps. So the first step, as we said, we are going to write the objective functions and also the constraint inequality. Objective function is C equal to 2s plus 3y. The constraints are these three conditions here, s plus 2y less than or equal to 10. Also 2s plus y less than or equal to 14. And x should be greater than or equal to 0. And the same thing applies to y should be greater than or equal to 0. So that's our first step. The second step, now we are going to graph both. So graph the solution of the constraint system. First, again, if the feasible region is closed and bounded, then we proceed to step 3. But if the region is not closed and bounded, then we have to check whether an optimal value exists. If not, we state that it doesn't exist, then we proceed to step 3. So again, to graph the solution, we know the two equations. We have two straight lines here. And the first line is here, and the second line is here. The intersection is right here. Now, based on the condition, we say only s and y should be positive. So we can see all the s and y value that are positive, nothing on the negative aspect, either down or to the left. So that's our second step. We plot our graph for the two equations, and also we meet the condition that the region will be bounded at when s and y are positive value. That's if they are greater than or equal to 0. Now the next step, we have to find the corners, the points. So find the corners of the resulting feasible region. This may require a simultaneous solution of 2 or more pairs of boundary equations. So for example, here, we may have the corners to be 0, 0, 0, 5, and here look like 2, 6, 6, 2. S value first before y. So here to be 7, 0. So again, those are the 5 possible. 1, 2, 3, 4. Actually, it's 4. So we have 0, 0, 0, 5. Then we have 6, 2. Then we have 7, 0. So when we get those 3 points, we are going to insert it into our objective function. So here they say evaluate the objective function at each corner of the feasible region determined by the constraint. We know the objective function given to us is C equal to 2s plus 3y. So 0, 0 means s is 0, y is 0. So we have 0. The second point is 0, 5. So we plug in 2 times 0 plus 3 times 5, which gives us 15. Then the next we have 6 and 2. So S is 6, so it will be 2 times 6. Y is 2, so it will be 3 times 2. The total give me 18. Then the last is 7 and 0. 2 times 7 plus 3 times 0, which gives us 14. Now here we say that if the two corners give the optimal value of the objective function, then all points on the boundary line joining the two corners also optimize the solution. But based on this question here, we can see the maximum value is 18, the minimum value is 0. So we can say that the function is maximus at when S is equal to 2, when S is equal to 6 and Y is equal to 2. This is when we have 18, that's the maximum. Then the minimum value will be 0. So when S is 0 and Y is 0, that's when we have the function is minimum. So that's the whole concept. Now let's see the second example. Here we have a farm co-op has a 6,000 acres available on which to plant corn and soybeans. Now the following table summarizes each crop's requirement for fertilizer and also harvesting labor hours and also available amount of these resources. So we can see from the diagram or the table, we have the corn and soybeans and also the available resources. So in terms of fertilizer, the corn will use 9 gallons per acre. Soybeans will use 3 gallons per acre. And we have 40,500 gallons available. In terms of the harvesting labor, with corn, we are going to have 3/4 hours per acre of harvesting of the corn. Now, soybeans, we have 1 hour per acre for harvesting. And available hours on our budget is 5250, which is 5,250 hours. Now, the question says, if the co-op's profit per acre are $240 for corn and $160 for soybeans, how many acres of each crop should the co-op plant in order to maximize the profit? And also, what is the maximum profit? Now, the second is if the market condition change so that the co-op's profit per acres change to 300 for corn and 100 for soybeans, how should the co-op adjust its planting to maximize profit? And also, what is the maximum profit? So let's start with the A. The A, we say we will let X equal to the number of acres of corn, and also Y will be the equal number of acres for the soybeans. We want the acres of S, corn is X, soybean is Y. Then the function that describes the co-op profit, this will be our objective function, because they say the profit is what? 240 per acres of corn. So corn acres is in X, so 240X, plus $160 per acres of soybeans, which is Y, so it will be 160Y. So we have our function now, profit P equal to 240X plus 160Y. Now the next step, based on the condition, they said X plus Y should be less than or equal to 6,000. That's the land constraint. They are variable. X will be the acres for, again, the corn. Y is the total acres for the soybeans. So they shouldn't be more than 6,000 based on the condition given to us. Let's go to the question one more. So we have the farm co-op as 6,000 acres available on which to plant both the corn and soybeans. So that will be our first equation here. The second equation also, we have 9x plus 3y is less than or equal to 40,500 y. Let's go back to the table so we can see the fertilizers for the corn is 9 gallons per acres, for soybeans 3 gallons per acres. So it will be 9x plus 3y equal to 40,500. That's the maximum available. So actually it will be less than or equal. We may end up using lesser or not more than what we have. So that's why we have the second equation, 9x plus 3y is less than or equal to 40,500. Then we have the harvesting time constraint. If you remember, they said 3/4 hours for corn and also 1 hour per acres for the soybeans. So we have 3/4x plus y, or 1y less than or equal to the total variable hours is 5250. Now, our condition here will say that X and Y should be at least equal to 0 or greater than 0, because S and Y, remember, they are the total acres. It's total acres. So acres of land cannot be a negative value. So now we finish. Now, the previous example, they gave us all these equations. They gave us the objective function and also the constraints. But here again, based on the application, we know the total variable land. X stands for the acres for corn. Y stands for the acres for the soya bean. And also we know the hours are the fertilizers, and also the hours of time available is 5250. Fertilizer available is 40,500. The condition said 9 per acres for corn, 3 per acres for again. So for the fertilizer usage, that's to be in gallons, sorry, gallons. So if we know this, then we solve our problem. Now we are going to follow the same step we did for the first question. The first thing we're going to do, we are going to plot the straight line for S plus Y equal to 6,000. Then the second one will be 9S plus 3Y equal to 40,500. When we plot these two equations, we have a third condition here also. Also, when we are doing the region, we have to make sure, we have to plot the third condition also. Then make sure our region will be only X and Y will be only positive values to again get the required region, the feasible region. Now, the corners of the points, we are going to insert it for, because we want to maximize our profit. This is our profit function. So we set the S and Y value to maximize it. So let's go through the process. You can see that we have 3 lines. Why? Because we have 3 equations. So that's the first thing we should take notice of. Each again line represents those equations. Now the second step, we need to again, well, first of all, when we are drawing the line, remember, same as the first example, we know this is inequality, but a straight line will be equal. So S plus Y equal to 6,000, 9X plus 3Y equal to 40,500. Then 3/4 S plus Y is equal to 5250. So draw those 3 lines, they are equality. Then the solution of the system of constraint inequality will form the feasible region for us. So here again, we may take any points. First of all, we can see that the S and Y only positive area because of the condition. The line didn't cross the Y to the negative area, or to the X to left, or anywhere, no negative value. Now we will take any points in the region area here to check. So for example, we may take any point 0, 0, or any points inside. Then we may check our condition. So if the condition is true, inequality is true, then those are the feasible region. So now we may use all the possible points insert into the profit function. The one with the highest will be the maximum or optimal profit. The one with the minimum will be the minimal profit. So let's go through the step. First again, we have the 3 lines graph. So this is what we have now. First, when we get the graph, we were able to get the region. Our region area is here. We plug in 0, 0 to any of the 3 equations. The condition was true. So we take any point. So here, how many points we have? 1, 2, 3, 4, and 5. So we take all these points and then we plot it. So those are the points. The first one is 0, 0. Then we have 4,500 and 0. 3750, 2250, 3000, 3000, 0, and then 5250, 5 points. Now, when we plot the points, we look for the maximum profit. The maximum profit here will be 1.2, so 1,260,000. That's the maximum value. The minimum profit, of course, will be 0. So here we say the farm co-op maximum profit is subject to the constraint In other words, the solution of the co-op linear programming problem is P equal to 1.26 million when S is what? 3750 and Y is 2250. So that's when the co-op plants, they will plant 3750 of acres of corn. And remember, Y is the soybean, so it will be 2250 acres of soybean. And this will achieve again maximum profit of 1.26 million. Now, B said if the market condition change so that the core profit per acres change. So here, all we can see here is that the profit function changes. So if it changes, that's fine. This is the new profit function, 300x plus 100y instead of, I think, 240x, instead of 240x plus 160y. Now we have 300 plus. So it's the same thing. We just plug in the points and we can find the maximum profit. So we plug in all the points, 0, S is 4,500, Y is 0, 3750, 2250, 3,000. Now we look at the profit. It seems like the maximum profit is 1.35. That's when the points have X is 4,500 and Y is 0, or when S is 3750 and Y is 2250. So here we say in this case, the maximum profit is 1.35 million, but it occurs either in the point 4500 and 4500 and also 0, or 3750 and 2250. This means that the function, which is the profit fund, the new profit function, will be maximized not only at these two corner points, but also at any other point on the segment joining them. So what we mean is that, well, let's go back to the graph if we can look at these 2 points. Again, we have 450, 3720. So 450 is right here. And so we can see the line here from 450 to 3750, 2250. Any point on this line will maximize because it's between these 2 points. So anywhere within it also will maximize our profit. So again, that's the maximum profit. And the next, we said the co-op has a maximum profit, as we said, 1.35 at any pair of points along the segment joining those 2 points, as we said, 4500 and 0 and 3750 and 2250. So let's see the next example. Here they say we should find the maximum and also the minimum value if they exist. Our objective function C equal to S plus Y. And the constraint is 3S plus 2Y greater than or equal to 12. So S plus 3Y is greater than or equal to 11 when S is positive value and also Y is positive value. So this is very straightforward. The first thing we do, let's draw the 2 straight line. 3S plus 2Y equal to 12 and also S plus 3Y equal to 11. And that's what we did here. We have the 2 lines. The intersection is where we get our result. Now we know X and Y should be only positive values, so everything is in positive area. Now our main goal now is to find the feasible region. So we may take any points below. Let's say we take 0. When I take 0, my condition here will say the answer will be 0 greater than or equal to 12. When I put 0 here, the same thing. So if one point is not feasible in this area, which is 0, 0, then any points here will not meet the condition. So we can move on to take any points here or take any points here or take our actual answer will be at this stage. So here we take a point like 0 and 6. We can see 0 and 6 will work because 6 is times 2 is 12. Is 12 greater than or equal to 12? Yes. Or 6 times 3 is 18. Is 18 greater than or equal to 11? Yes. So we can see 0, 6 is outside. That's why if one point in this area meets the 2 conditions here of these 2 equations, then all the area will be feasible region. And that's what we have. Now, if you know the feasible region, we need the corners now, the points. So we have the first point here is 0 and 6. Second point is 2, 3. And the third point is 11, 0. So we are going to plot these 3 points in our objective function, which is c equal to x plus y. So we're going to get c equal to 0 plus 6. And also, so 0.6 will give us 6. And also 2 plus 3 will give us 9. 11 plus 0. So the maximum will be 11. It will be 11. So let's see. So that's what we have, c equal to x plus y. So the first c will be 3. And the second c will be 5. And the next one will be, why is it 3? Because again, here we say it shows that the solution region, the graph of cs plus 4, c equal to 3, 5, and 8 will give us the solution. And those are the points. Now we take the 0, 6, 11, 0, 2, 3, and we should get the solution. So this is the 2 equation we're trying to solve. It uses a system of linear equation. So we get our point 6. And the next point will give us 9. Oh no, sorry, 11. And the last point will give us 5. 2 plus 3, 5. So our conclusion, we said that the minimum value, of course, will be 5. Looking at here, 5 is the minimum and the maximum value is 11. Actually, here we say the maximum value x plus y does not exist because we have some open boundary section. When we look at the graph here, we say I look at the maximum value straight, but first we always need to look at the graph also. So we have an open bounded, it's not close. This can be open, can stay expanding out. But if it's here, it will end close. And actually it's a spring somewhere. So we conclude that the minimum value is this, but the maximum value x plus y does not exist. We should know that C can be made arbitrarily large in the feasible region because it's open. It's open. So again, that will be the end of our first section of linear programming course. Again, here we are using a graphing method. We're using the graphing method. Again, if you have any question, please post it in our Blackboard and I'll be ready to answer the question. Or you can wait in our next section. You can also send by email or our next in-class section. But if you need your answer as soon as possible, then again, post it in the Blackboard. Thank you. Or any question about the homework also.